All right, let's dive in. We're about to take a pretty cool leap, from the comfortable world of algebra that we all know into the really powerful world of calculus. We're going to build a bridge from measuring averages to capturing a single perfect moment in time.
So let's start with something you see every day. Have you ever been driving, glanced down at your speedometer, and really thought about it? How does that thing know your speed? Not your average speed over the last 10 minutes, but your speed at this very second. Well, believe it or not, the answer isn't just some clever engineering. It's actually the very beginning of calculus. Yeah, that simple dial on your dashboard is doing some seriously advanced math, and by the end of this, you're going to get exactly how it pulls it off.
Okay, so before we jump into the deep end, let's start somewhere we're all comfortable, right? Let's go back to good old algebra. This is the world we know, where we're used to measuring how things change over a period of time.
You remember this, right? In algebra, if you want to know how fast something's changing, you find the average rate of change. It's pretty straightforward. You pick 2 points in time, draw a straight line between them on a graph, that's called the secant line, and the slope of that line, boom, that's your average speed. Let's make this super concrete. Say we've got a simple function, f of x equals x squared, and we want to find the average speed between, say, 1 second and 3 seconds. All we do is plug in the numbers. We figure out the change in position, which is f of 3 minus f of 1, so that's 9 minus 1. Then we divide that by the change in time, which is 3 minus 1. Simple math, right? We get 8 divided by 2, and our average rate of change is 4. Easy peasy. But here's where things get tricky. That average speed over 2 seconds, that's not what your speedometer is showing you. It's showing you your speed right now. And suddenly, that's a completely different kind of problem to solve.
So here's the real catch. Our trusty algebra tool, the slope formula, absolutely requires 2 different points. But for an instant, well, an instant is just one single point in time. If you try to plug just 1 point into our formula, you end up trying to divide by 0, and boof, algebra just throws its hands up. It can't do it.
And this right here, this is the exact moment we need to make the leap into calculus. To solve this puzzle, we need a brand new, incredibly powerful idea. And that idea is called the limit.
So let's just pause and look at this massive shift in thinking. On one side, you've got algebra with its average rate of change, using 2 points and that secant line. And on the other, you have calculus, aiming for the instantaneous rate of change, focusing on a single point and using something called a tangent line.
So what is this limit thing? Well, it's the absolute key. Picture those 2 points from our secant line. Now, imagine you start sliding 1 point along the curve, getting it closer and closer and closer to the other one. The distance between them is shrinking, getting infinitely small. The limit isn't about what happens when they're on top of each other, but what value the slope is approaching as they get ridiculously close. It's this clever trick that lets us find the slope at a single spot.
Okay, so now that we have this idea of the limit, let's see what we can do with it. This is our brand new tool, and it lets us calculate the rate of change at any single moment we want.
And there you have it, the instantaneous rate of change. It's just the slope of the tangent line. You know, that one line that just kisses the curve at a single point without crossing through it. And this special value, this slope at a single point, has a famous name, the derivative. Congratulations, you've just been introduced to the absolute heart of differential calculus. All right, let's go back to our friendly function f of x equals x squared. But this time, instead of an average, let's find the exact instantaneous speed at the moment x equals 2. So what do? We take our slope formula, but we apply the concept of the limit. We imagine that second point getting infinitely close to x equals 2, and we just watch what value the slope starts honing in on. And what number does it land on? It lands on 4. Now, this is kind of a cool coincidence in this example. Remember how the average speed between 1 and 3 was 4? Well, it turns out the instantaneous speed right at x equals 2 is also 4. We've done it. We've found the speed for right now.
Okay, let's bring this all the way back home. Let's connect this powerful new idea back to our original question about the car and that speedometer.
So that speedometer in your car, it's not bothering with average speed. It's basically a real-world derivative calculator. It is constantly, in real time, calculating the limit of your change in position over an incredibly tiny change in time. It is quite literally showing you the derivative of your position from moment to moment. How cool is that?
Now, as you start playing around with this new power, there are a couple of common wrong turns people take. So just keep this in mind.
Average is always about 2 points. That's the algebra way. Instantaneous is all about 1 point, and you get there using a limit. And seriously, don't forget that the limit is the magic ingredient. It's not just about a difference, it's the limit of that difference that gives you the answer.
So, let's just quickly recap the journey we just took. We started with a simple secant line from algebra, the one that just cuts through 2 points on a curve. Then, by using this amazing tool called the limit, we transformed it into a precise tangent line, a line that tells us everything about a single exact instant.
And that leaves us with one final, really big thought. We've just unlocked the mathematics of right now. And if we can use this power to understand a car's speed, what else can we understand? What about the growth rate of a business, not over the last quarter, but at this very moment, or the exact velocity of a rocket as it leaves the atmosphere? Think about it. The possibilities? They're pretty much endless.